I think we're live. Double check.
Checking. Usually takes a little bit of time. Yeah, we're live.
Okay. Well, hello everyone, and welcome to the new year, 2025, and a brand new episode of Courtcast. I am your host Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast for and kicking off the new year. Gonna start off things strong. Before we get to that, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So, Tim and Mikey, this is an interesting episode. Um, I guess I'm thinking the best way of like kind of starting things off. So when we do typically do physics, it's always done in the context of space and time. From Newtonian or classical physics to Einstein's theory of general relativity, there's this notion of just space and time. It seems so intuitive to us that we move through the three dimensions of space, and then there's of course a dimension of time. And so it seems a bizarre question to me to even ask like can we do physics without space and time? The thing that like the things that you're studying are like embedded in. So I guess, I just want to let you guys give a few words of like the motivation of why we're even exploring this question, and then we can get into the meat of it.
So we first do the
I
short
guess,
version.
yeah, short version.
Yeah,
And I do want to hear from Mikey because Mikey looks excited.
yeah. I think the real short version is it is well known that there's a collision between space-time and quantum mechanics. Einstein proposed the idea that space-time is a fabric, but quantum mechanics kind of completely destroys that. It tells you that things are always fluctuating in and out. The two are in conflict. And as we know, the world is fundamentally quantum mechanical. So probably quantum physics has the upper hand there. So space-time must be quantum mechanical in some ways. And if it is quantum mechanical, then what it fundamentally is has to be different from the way we perceive it. Where we perceive things happening in a location at a given time. But if you zoom in, that should get modified by quantum physics. And this has been the driver for theoretical physics research, I think, for a long time. And people are always looking for, if not space-time, then what else? And I think it seems like there should be an answer, and hopefully some of the research are getting closer to the answer.
Got it,
Yeah,
got
why,
it.
why would we want to get rid of space? It's like like thinking about the universe in terms of space and time is super useful for humans, right? It helps us understand our relationship with respect to each other, our relationship with respect to the rest of the universe. It's all kind of like in this language of space and time. And that starts it starts before we're even born, right? Psychological studies have shown that we're essentially born with an understanding of spatial distances and concepts of objects existing in space and time. And I mean, I was just trying to think, is there any concept that is more fundamentally ingrained in our heads than space and time? I don't think so. We're born with, it's psychological research has also shown that we're born with some like pre-programmed sense of language and intonation in terms of what sounds aggressive and what sounds friendly, for example. But even that is probably not nearly as ingrained in our head as this concept of space and time, right? Like ever since the very first organism started to develop, there was probably evolution in favor of understanding the world in space and time just because of the advantage that it gives you to be able to do that, like evolutionarily, right? So um, it's been so good to us, and now, yeah, like Sahil, you said, now we're proposing the idea of trying to do physics without it. Like, why would we want to do that? It is a
Yeah.
fun question. And yeah, it's just to reiterate what Tim said in terms of like the reason for why you might want to get rid of it. And it's a pretty recent development, right? Like no one's had any complaint about the idea of space and time for there was no complaints about it, right? No reason to want to try to get rid of it until the theory of quantum mechanics came about. And actually, even after quantum mechanics, after the theory was laid out, it wasn't appreciated for many, many decades. But you know, a more modern analysis of quantum mechanics argues quite conclusively that the idea of space and time as we know it, and you know, distances between objects being the smooth parameter, that is fundamentally inconsistent with the basic tenets of quantum mechanics. And this has led to the strong suspicion amongst most of the top researchers that space and time is an approximation of something else more fundamental, and that this picture of space and time only emerges when you sort of zoom out of the picture, kind of like you look at a photograph close up at the pixels, right? It doesn't look intelligible as a photograph, but you have to kind of zoom out and get a big picture of it before it starts to look like a photograph. So in the same way, we believe that space and time might be a so-called emergent property of the universe.
Yeah, I think that that segues nicely into how we'll start things off. So I want to lay the groundwork and you know, have a shared understanding of like what is space-time. I mean, there's this fabric notion, but like let's just start by defining what it is. So I guess, Tim, I'll point this question at you.
Yeah, I think in physics it's very intuitively defined. It's just taken as an axiom, right? Like everything that could happen has to happen at a given location and a time. It's just is a given. Like I throw a ball up in the air right here, you know. And in probably not even until you go to like graduate level physics do you even get a hint of going away from that axiom. So I would say it's just defined axiomatically. These are just numbers that you feed into the system.
It's a coordinate system, if you like. Yeah,
exactly. Yeah, it's a system. It's a given. It's as fundamental as 1, 2, 3. Like what do you enter to the calculator to do calculation? Like you got to put in something, and space-time to us is as fundamental as that the unit in which to do physics on, right? But I want to emphasize that if you look at it physically, it's funny that we actually never truly experience space-time exactly. You know, like how do I know my hand is there? How do I know my finger is here? It's because the electrons are interacting, and we like to think that the electrons are interacting here, but we never directly feel that it's here. You know, I see my hand is here because photons are hitting the electrons, bouncing into my eyes, and I sense something, right? But like, even though it's so axiomatic, the space and time, and we very intuitively feel it, the interesting thing is you never directly confront with space-time itself. It's always somewhat indirect.
Yeah, that makes sense. I guess you know, Tim, one thing I want to I guess mention that you had mentioned earlier was you had said, oh, like you know, quantum mechanics isn't compatible with this notion of like this smooth fabric of space and time. But I remember when I was learning quantum mechanics, you still had the notion of space and time. You have the wave function, or you know, whatever quantum mechanical object you're looking at that exists in like space and time. So when you talk about like quantum mechanics being incompatible with this, like, you know, with space-time itself, could you expand upon that?
Yeah, I would say, you know, when the quantum physics that you learn in college, it's probably a bit of a Frankenstein quantum physics. It's not the full version of quantum physics yet, because it looks at particles as quantum mechanical, but it doesn't look at the entire world as quantum mechanical. If you were to really do quantum physics entirely, gravity itself has to be quantum mechanical. So even the location itself becomes quantum mechanical. So really the conflict comes when you try to throw gravity into the quantum mechanical realm. And we can briefly recap this notion that when you combine space-time and quantum physics and gravity together, space-time kind of destroys itself. And there's this black hole argument that we can go through, and you can see it from the physics itself is telling you that, hey, space-time is broken. Like it ceases to exist the moment you try to like really get at it, basically.
Yeah, it's a little subtle to relate this current discussion to the kind of quantum mechanics that you learn in college. And you have to remember that the kind of quantum mechanics you learn in college, space and time is as Tim mentioned, it's already an assumption. You're already assuming that some space time exists first, and then on top of that, you're trying to do quantum mechanics. But if you take this to its certain logical extremes, if you assume that there's a space-time and you assume there's quantum mechanics on top of this, there's certain logical extremes in which you find that the quantum mechanical interactions actually destroy the space-time itself. So you put it in as an assumption, and you see that at a certain logical extreme, that attempt to put them together in the usual way leads to, well, not only all kinds of paradoxes, but also it's the destruction of itself, its own structure.
Yeah. So Mikey, both you and Tim have mentioned, separately that if you combine all these things together, space-time will destroy itself. So can you walk the audience through an example of like what happens if you just let's go to the extreme? What happens? What's the worst that can happen?
I think the first thing to remember before we go through this argument, though, is that when I think of like the universe that I live in, you can think about it as like a space, right? As like a box that we live in. But a more proper way to define our universe in terms of physics, or let's say Sahil's universe, is like what is the collection of all the objects in the universe that I could possibly gain information about or interact with in some way. Let's say that there was some region of the universe where it was just fundamentally, in principle, impossible to extract information from there or interact with it in any way, right? In a sense, even if you could say, okay, it shares the same spatial overlay, it exists in the same space as their universe, but is it really part of my universe if I am fundamentally, in principle, blocked from any kind of interaction or exchange with it? And in physics, we would say, no, it's not. Like there are certain instances in which that's true, but we don't have to get into those details. But so that's the first thing. The first thing is that for something to exist in our universe, we have to, at least in principle, be able to interact or extract information with it. And then the second thing that we have to remember for this argument is that if you want to extract information about a smaller and smaller region, it requires more and more energy. So in optics, this is important because, like, if you're trying to get like a high resolution image of something small, you want to use light that has a higher wavelength. So, like, literally, if I use a blue light to look at something versus red light, blue light has a smaller wavelength. My resolution will be better using blue light. But the consequence of that is that blue light is more energetic. And so the smaller you want to look at something, the higher your probability is of destroying the thing that you're trying to look at. And so, yeah, those are the first. I think those are the two prerequisite facts to understand about the universe. And then, I don't know, Tim, you want to describe the black hole thing?
Yeah, I mean, the last ingredient is gravity, right? If you put enough energy into a small enough location, you make a black hole. And unlike all the other ways of probing things, you can send another particle in. You can argue maybe my apparatus is not good enough. Maybe I can have a more precise, apparatus, more precise calculations. But when gravity gives you a black hole, it's game over. Basically, there's nothing you can do. It basically destroys itself. So the whole argument is that it's almost like finding a bug in the matrix. Like if the universe is the matrix and you go through this step to try to figure out what the space-time is made of, you make a black hole and the black hole destroys itself. Like it destroys that location. So it's telling you that this is basically you're seeing a glitch in the matrix, right? Like it's telling you that something is off. Like the space-time as we know it is not exactly what it seems. Like there's some inconsistency if you view it the way if the way we view space-time can be taken to the extreme, it leads to just self-contradiction basically, and it tells you that therefore space-time must be different at some point when you zoom in further and further and further.
Yeah, said that another way, any attempt, even in principle, to extract information about our universe below a certain length scale will inescapably lead to the creation of a black hole in that region, which is the fundamental censored about, like, yeah, we can't extract any information from a black hole. So it's almost like, you know, the short distance layer of our universe is somehow like disconnected from our universe. It's like a whole different thing that we don't understand yet.
One question I wanted to ask, kind of devil's advocate of this, is we've never been able to do this before. I mean, I'm assuming the energies that you're talking about are much, much higher than like what we can possibly generate at this moment. So I guess how can I take this argument at face value? We've never done this. Like, we don't even understand how like black holes like truly form. Like, I mean, they give the argument that, oh, enough mass comes together, it like crushes upon itself and then it becomes a black hole, but no one actually knows what that entire process is like. So I'm wondering, like, is there room that this could be wrong, or like any changes, or like, is this, I mean, solid theoretically, or I just want to understand that more, limitations.
Yeah, it's tough. Yeah.
I would say there's no way out of this, right? If you assume Einstein's theory, and let's say this doesn't happen, space-time doesn't destroy itself, then Einstein is wrong. Then that means we don't have a full theory. So either way, we're missing something. It's just telling us that either our theory is wrong, or if our theory is correct, the space-time will destroy itself, and therefore it must also be wrong. So there's no scenario in which our theories, as it is right now, is fully correct. It's just not logically possible. So either way, something is up with space-time.
Yeah, it is tough though. It's tough to try to give the audience, I think, for a sense for, right, like when you have experimental evidence for something, for most people that's like the threshold for quote unquote proof, even though science doesn't prove anything. That's a whole different discussion. Science isn't in the business of proving or disproving things. It's based on a complete misunderstanding. But so when you have an idea that your theory says must be true, but let's say you can't probe it experimentally, one way to judge it is like to take, as you said, take the devil's advocate. Like, in what way would our current theory have to be wrong to accommodate the fact that this doesn't happen? What we know is that there's a threshold for how much, what we think we know is that there's a certain amount of energy you can pack into a small enough region. After that point, you'll get a black hole. Like that, we're assuming that is true. And we've seen this astrophysically, never with something as small as like the kind of black holes we're talking about, but across a wide range of black holes, like Chandrasekhar famously, predicted the threshold that would require for this to happen astrophysically, and that's been confirmed, across many different scales. Maybe all of this is true, like we observed, but maybe when you get to really, really small distances, the rules change in some way. As Tim mentioned, that's kind of what we're saying happens anyways. That space and time starts to act radically different. But okay, maybe you say that, okay, but space-time looks roughly the way we think it does, but something happens that prevents black holes from forming at these short distances. You can bend over backwards to try to accommodate this, but in the end, you find you lose a lot more than you gain from this exercise. Like, you might be able to cook up a scenario where we can keep our normal version of space and time, and it doesn't tear itself apart. But in the process, you'll be forced to throw away, hundreds of years of well-established things about the same theory that we know are true. And so it's about confidence in the argument. Let's say.
Yeah, no, that's yeah, that totally makes sense. So okay, so kind of taking a step back, we've discussed how, I mean, and also for viewers who are interested in more about this, we do have an episode very popular according to who have those who have watched it. Space-time is doomed. So those who are interested, please check that out. So now we've talked about how the notion of space and time itself is emergent. It's not truly fundamental. I'm wondering then, can we talk about like where does that leave physics? Kind of what is the point of physics like? Because everything we do is embedded in this space and time. We don't have nearly enough like energy to probe, at these scales, so that space time would destroy itself, based on what you're talking about. So I'm wondering, what is the point of physics in that case, if this is like bunk?
Yeah, I would say, if you follow this logic, if you truly believe that space-time is not fundamental, then you need to find some alternative. And the first step any good physicist should do is, can you rewrite the laws of physics without mentioning space and time? That will be the first step. You're not even trying to invent new physics yet. You're trying to say, hey, can the laws of physics be told without space and time? And the answer, surprisingly, turns out to be yes, although only in limited cases. And this is still very active research. But although this is also not very new, I think on around 2013, it's almost a decade old now, physicists have cooked up with a toy model. But when I say toy model, I don't mean like a trivial model, like a ball going up the air and falling down. No, this is a still very complicated theory. But a toy universe where, even though the universe does have space and time, but the underlying physics of it, can be described without any mention of space and time. And that's what they've achieved. And since then, there's a lot of development, but this is sort of the first, I guess, one of the first times that it has been done. And I think we can say the word, that program, at least the object that physicists discover, is called the Amplituhedron. And somehow that object, can replace mentions of spacetime. So instead of mentioning spacetime, you can say, well, let's look at the Amplituhedron.
I guess, Mikey, I'll point this question at you. So, we're talking about doing physics. Can you take the current set of equations in physics and replace them, or develop an equivalent set, but have no mention of space and time? What are these equations doing? Like, what are they computing, or what is all this machinery for, is my question. Like, what are we doing with all this?
Yeah, that's a good question. So if we think about just normal physics, like, right, the kind of physics that we all learn in high school, and some of us continue to learn in college, you ask the question, what is a physics equation computing? Usually, especially in high school physics, like, you have an object that's here, and you have, there's some state, there's some forces acting on it, and maybe other objects acting on it, and you ask the question, where will it be in 10 seconds? If there's force of gravity is acting on it, you can calculate where it'll be. If it's colliding with another object, you can calculate that too. So we're very used to thinking of physics in terms of, like, this object is here now, where will it be in 10 seconds, or something like that. But there's another way to sort of think about the laws of physics, and in terms of, like, what it's computing, right? You can also think about it as computing, like, I have a bunch of stuff at the beginning. Let's say I have, like, a bunch of particles with some momentum and some initial state. Something happens, like, some interactions maybe, or, something that we might call, like, motion or traversal through space. And then at some other time, there's 10 particles. You could also ask the question, what is the relation between the inputs and the outputs? And in quantum mechanics, everything becomes probabilistic. So the fundamental question you ask is, what's the probability that I start with 5 particles, let's say with this momentum, and then I get 10 particles going out with that momentum? right? And I can sort of think of the first problem as a iteration of the second problem, right? Like if I know every particle is in and out, right, I can imagine subdividing time and just computing a particle's motion through space and time as the sequence of these in and out interactions, right? So yeah, so normal physics typically computes trajectories through space and time. In particle physics, we think of a trajectory as sort of a collection of sequential interactions. And the fundamental question is, something goes in, something goes out. What is the probability that something goes in gives you something that goes out? And that object that we use to calculate what we call the in states and the out states is really all you need to describe everything that happens in the universe. And in quantum physics, for whatever historical reasons, this object is referred to as the amplitude. And so that also kind of explains the name. This most recent program kind of attempts to go beyond this, right? And I just want to also just back up a little bit, and there's a kind of a deep connection between momentum and space, right? Like even though I know the incoming, let's say I have 5 particles going in, 10 particles going out. If I know the momentum of each incoming and outgoing particle, right, then infinitesimally I have some sense for their spatial trajectory, right? Without talking about space, though, just by talking about their momentum. Then when I integrate the momentum over many sequences, then I start to get a notion of space. But if I just think about an instance, let's say, and I think about the amplitude for this one instance, then I don't need to talk about space and time at all. All I need to talk about are momentums, just vectors and directions. Then I can build space-time by thinking of this as a sequence. So this is the object that's kind of instantaneous in, out. That's kind of the fundamental object that we view the universe as computing. And this is the object that people are trying to generalize in terms of writing down all of physics without reference to space and time.
I think
I just want to say a shameless plug again that we have another episode that discusses this object Mikey was talking about, amplitude, much in depth. So do check that out. All right, sorry, go ahead, Tim.
Yeah, I think a good way to think of it more simply is the amplitude is almost like a directive, like a recipe for things to happen. It's telling you that, hey, 3 particles, you over there, you're gonna go this way, and there's this probability you go that way. It's sort of, and every interaction, like a ball moving up and down, you can break it down into these tiny little minuscule directive. A particle was directed to go this way and then go that way, and then left, right, up, down, whatever, and then causing the ball to move. This is a very reductionist way of thinking about a physical process, and in particle physics, the amplitude can be viewed as the fundamental thing it's computing.
Yeah, that makes sense. I want to jump to an audience question about something we discussed earlier. And they're saying earlier it was discussed that in our observable space-time, the problem seems to be the closer we observe it seems to destroy itself because of how energy works, question mark. My question is, does the same not apply with the amplituhedron?
Right, yeah. So the hope is that if you don't mention space-time, black holes are okay. You only look at what goes in and what comes out. Who cares if there's a black hole there? Because I don't need to know. I only need to know the directive of what happens. It's only if you insist on saying, hey, where is my particle? Let's say I'm so hung up on the idea of space and time. Like my money's on space and time. If it ceases to exist, I will be very unhappy. Whatever, right? Like I'm betting my money on it. Then you need to prove that space-time is there. But then you gotta really pinpoint it. Like, how do you pinpoint space-time? How do you grab a pin and just pin it down and be like, this is my space-time? And to do that, you gotta shoot a lot of energy at that location, and at some point a black hole gets created, and then it disappears. It's like the harder you try to get at it, the more it goes away, basically. But the if you instead don't think about space and time as all that fundamental, you only care about amplitude, things going in, things coming out, then it's okay. You can have more things coming in, less things coming in, and see things coming out. There isn't this let's say like this singular problem. You won't run into like destruction, I guess.
Yeah,
Hmm.
just to be clear, like it's not guaranteed that this research program will work, right? Like there is some possibility, some that let's say this research program is completed successfully, and then they find, oh, the problem is still there, but it just maybe just manifests itself in some different way. But it just seems like this paradox that people have been thinking about, space and time destroying itself. It's clear that the point of failure here is the smoothness of space, or at least we believe it's clear. So if you can rewrite the theory, removing the point of failure, there is some of it is faith, hope, or expectation that it will lead to at least some deeper insight. Even if it doesn't solve the problem, hopefully it'll lead to some more insight about the inner workings of the nature of this problem,
Yeah.
for example.
Yeah, let me also add that we haven't described what literally an amplituhedron is yet. We probably won't have time. We might not even have time today. But the thing is, yeah, like Mikey said, amplituhedron itself could be inconsistent. And indeed it is. It can be consistently defined for a very specific subset of theories. So we don't truly believe amplituhedron is the full answer. But the fact that for some toy universes, such a thing exists that can replace spacetime, that's huge, basically. Like otherwise, like how do you even replace space and time? That seems like really, really, really hard. The fact that it can even be done in some limited cases is tremendous. It means that maybe our universe is not. Maybe our universe, if you remove space and time, is not described by amplituhedron, but it's got to be something like it. It gives us a hint on what the ultimate truth may be.
I guess can we give some basic ingredients about like what kind of goes into it? Because I think common human intuition would just have trouble grasping at like what does it mean when you don't have space and time? Like the two things that I know really well, as Mikey was talking about. So can we maybe give some intuition around it? And maybe if possible, intuition around the name. Like why is it called amplituhedron? Why not just amplitude?
Yeah, I can take a stab at this. So the name the hedron comes from a relationship to the Platonic solid. I think those are called something hedron. Because all the Platonic solid has it's something drawn, right? So
Except for the cube.
Yeah,
Is there a hedron name for cube? Is it called like a quantum hedron?
maybe, yeah. And I think initially the way people discover this is it's a bit of a surprise. It was not clear that you can do this, but physicists were just kind of poking around and finding structures in these theories. And we can get a flavor on why Platonic solids are even involved in an object like this. So the logic goes like this. Imagine you have a theory where every particle is moving at the speed of light, right? And trust me, this simplifies the theory a bit, right? And then if you look at all the processes where particles come in and particle goes out, you can kind of visualize in your head. When particles come in, it traces through a line, just like how light goes in a straight line. So there are a bunch of lines coming in, a bunch of lines coming out. And if you visualize this is kind of like a geometric object. There are these lines, and then some of the lines might intersect. And the way we think of space-time is that, interaction happens when particles meet, and this is the principle of locality. Like my hand can't just, poke Sahil, like, I don't know, a few hundred miles away. Like this is the principle of locality. I can't do that. So to sort of mark up this concept of locality, you have the principle that particles cannot talk to each other unless they intersect, right? So basically you have a bunch of lines that intersect. So it's kind of like a geometric shape. Now here's a good analogy, but it's not exact. But I don't think it exists anywhere in the internet. But if you study a little bit of Platonic solid, let's say you take a cube, right? You know that there's the perfect alternative Platonic solid that can be inscribed inside the cube. If you think of it a little bit, each side, let's say you put a vertex on each side. So the solid that can be inscribed in a cube is a octahedron. And you can do the same thing with the isocahedron and the thing that can be inscribed.
Wait,
Yeah.
Tim, can you define the word inscribed?
Basically, it's a perfect shape. I mean, it's a little technical, but if you take a cube and you put a dot in exactly the middle of each side, and you
Okay.
turn them into lines, and you connect the dots, you will form another platonic solid. You know, and that's an octahedron. It's like two pyramids stacked on top of each other. And roughly speaking, that's what amplituhedron is. It is to take the shape of particles going in, intersecting. When they interact, they intersect. There are these dots. You imagine that picture, draw them out, and then you sort of take this dual perspective. You for each line, it's not exactly the same, but for each lines of particles, for each line the particle traces out, you turn it into a dot. Every time they intersect, you draw a line. This turns into a really weird abstract space called the twistor space, but we're not going to go into details here. But in this space, the shape, you can form these shapes. Particles interacting becomes these shapes, and it turns out that in this very specific theory, the volume of these shapes is the amplitude. And that's not obvious at all. But it turns out that physicists discovered that that's literally what it is. And that is the discovery. And it found that, hey, look, you can actually look at amplitude without ever talking about space-time, but these geometric objects in this really weird twistor space. And when you calculate, if you reduce physics to these directives, just like particles, U3 particles go from A to B. These directives are basically computed by volumes of these geometric objects. That's the crux of the amplituhedron.
So what you're saying is maybe it might be helpful to, like, I guess, describe really briefly, like, if you're a theoretical physicist and you have particles coming in, some stuff happens and they come out, what would be kind of like the amount of work you would have to do versus if you use this technique and look at, like, you convert it into maybe some different abstract space, you compute the volume of this object, this really abstract object, and then you get the answer. So maybe that might help the audience understand, like, better.
Yeah, I would say at least in terms of research direction, like when people discover the amplituhedron, in some sense they haven't discovered anything new, right? It's literally a different way of looking at a system. It's almost like, instead of looking particles coming in and out, you can look at these geometric shape, how large they are. But the answer is the same. You get the same answer. So in some sense, they're not doing anything new. They're just reinterpreting what's going on. But it's very palatable because traditionally, when you do calculation in quantum physics, remember the other episode we talk about how amplitude is the sum of all possibilities, right? And sometimes this sum is really large. The traditional way of thinking about this is, let's say I want to calculate when two particles of light comes in, what's the chance of getting two electrons going out, right? To do that, I have to look at, well, two light particle comes in, maybe they will collide at location A, B, C, D, or maybe they will collide 1 meters away or 2 seconds later. You have to sum up all these possibilities. Or maybe they will come in, some other particles get created, then they destroy again, and then form electrons and positron pair. So traditionally, if you involve space-time, you might have to do a bazillion sum. In fact, that sum gets exponentially large the more precise you want it to be. And that's the Feynman diagram approach. It turns out that that's really, really laborious. Sometimes you have thousands of terms, right? And the interesting thing about the amplituhedron is, and there's a famous calculation where you have 5 pages of just very, very complicated calculation. And at the end of the day, it's simplified to one line, one term. And people were like, oh my God, that's crazy. Like, how is there so many cancellation? It's almost like you're doing calculations in a really roundabout way. It's like 1 plus 0.1 minus 0.1 plus 0.2 minus 0.2. Like, what are you doing? Just say it's 1. But when you use amplituhedron, what you get is you skip straight to the answer. That's what's beautiful about it, because when you calculate the volume of these amplituhedrons, you just write down the answer, and that's what they discover, and that's why it gives people a strong belief that they're onto something. It's just this theoretical evidence. Like, it's just like, oh my god, it's just so much better, even though it gives you the same answer, but it's so much cleaner. It gives people theoretical oomph. Be like, hey, we're onto something here.
Mm-hmm. And just to be really clear,
an aesthetic appeal to it. Yeah, sorry.
Oh no, I was saying just to be clear, there's no like new physics. It's just a different way of doing the physics that currently is there at the moment.
That's right. Yeah. I believe people haven't really pursued the question of like how this actually resolves the paradox, so much as there's so much work to do in terms of you know, figuring out what the hell this thing is.
Yeah. Yeah, I would say this is the first step, right? Like they still haven't solved the problem, and also and maybe going back to the audience question. So these theories still don't include gravity yet. So if you include gravity, yeah, there's still this self-contradiction where, you know, if you put too much energy, you make a black hole. But they kind of just ignore that. The next step, of course, will be once you realize how amplituhedron work. Because right now, it's the same physics. They're not doing anything new physics. It's just a different way of calculating the same physics. But once they understood that, the hope is you can go beyond now. You can generalize from the angle of amplituhedron and maybe create a theory that has no analog, that cannot be written in the conventional way. And then this may be ultimately lead to a quantum theory of gravity. But that has not been done yet. That's speculation. But this is how research is, you know. You have some hint that it may work, and you keep going at it.
And so this implies that the amplitude object, the object that we're saying that the only object that the universe is actually computing, which is related to the probability that I have some starting state of particles, they go in, some stuff happens, whatever happens, and then some output state of like a different set of particles or maybe the same particles. That object, the amplitude, is essentially space-time independent, is what they're essentially showing.
Yes.
It can be in these certain cases.
Yeah.
Okay.
Yeah.
Okay.
Yeah, exactly.
Yeah. And then I wanted to get a bit more intuition around like, so you're essentially replacing space-time with a abstract geometric type of picture, or what are you essentially like replacing it with? I understand you're talking about this dual space and this inscribing and stuff like that, but is there a simpler analogy that we can lean on for this?
Yeah. I mean,
sorry, go if you have a better answer.
yeah. Well, I mean, in some sense, in these toy theories, space-time is still there, but they're just not referring to it exactly, right? It's almost like I guess an analogy I can think of is like, imagine you're swimming in the ocean, and you're like, well, where am I in the ocean, right? Of course, if you have a GPS, you'd be like, exactly, this is where I'm at the ocean. On the other hand, probably a more reasonable thing to do is like, you feel the water hitting you, and then you kind of can gauge, like, hey, look, this is where I'm at, you know? The amplituhedron way of thinking is that, you know, at least at its core, it's the thing that the scattering, the particles coming in and out, this is the fundamental thing. And when this happens repeatedly, when you feel water molecules hitting you, when those add up, it gives you a feeling of being in space and time, right? So space and time still exists because out of these geometrical shape, particles can only interact when they are close to each other. This is still, you know, this law will still come out, and this gives you an illusion of space-time. But then it's not taken as an axiom now. Like the feeling of space-time emerges. It's not taken as a rule. So that's what you get. But the physics is still the same. You know, so at least so far in that program.
Yeah, I would
Yeah,
say we touched upon the answer to that question earlier, whereby like what we're really doing is we're saying that physics isn't about computing trajectories. It's about computing a sequence of directives, as Tim called them. So maybe the universe, instead of thinking about like, yeah, in terms of objects floating around, it's just a sequence of different directions, possibly, maybe that's consistent with some people's idea of it being one big computer. And that's not new either. Like that's the same idea as the amplitude. It's just that typically we take the amplitude, the sequence of directives, and then we interpret it as a space. But so if anything, this basically just reinforces this idea that we already had, that it's not only you can think of the universe as a set of directives, but you have to think about it as a set of directives at a certain, at a certain level.
I guess one thing I want to understand more about is in this amplitude object, you have an input state and then you have an output state. But let's just look at the notion of a state itself. So a state, in my mind, without referencing spacetime explicitly, is like a collection of particles. But how do I think of the notion of a particle if I can't think of space and time like localized? Like the particle as a notion of me naming something. In order for me to name something, it needs to be separate from everything else. So I guess how do you think about this in the concept where there is no space and time?
Yeah, I kind of briefly touched upon this before, but it has to do with the relationship between momentum and space, right? So instead of talking about
Mm,
the position of a particle, you can
mm,
equivalently talk about its momentum. And if you have a sequence of momentum, if you have a sequence of particle
mm,
momentums, right, like you can integrate the path and then figure out how much space it traveled. But that requires you looking at more than one directive at a
mm,
time. A single directive we can think about just in terms of just a momentum vector, which gives you a magnitude in some direction
mm.
of motion. Um,
But if mhm. What one question I have regarding that is like regarding momentum. Momentum is, I mean, at least from classical physics, is defined in terms of like space and time.
yep,
It's it has a velocity term in it,
yep,
which
yeah,
involves both space and time in it. So
yeah.
it seems like a really roundabout way of, of getting like, but you're still using space and time, even if
Well,
you're using
yeah, yeah.
momentum. So yeah,
Well,
so
Tim said, yeah,
I'm
just
wondering,
where
yeah.
that dual space comes into play, right? Yeah. So
Mm,
in order to get rid of space, first we get rid of like, the obvious notion of locality. So in a sense, we're trading space for 2 points in space, right? Because that's what defines the
mm,
velocity, right? So first we trade space for
yeah.
2 points in space. Then we
Mm,
realize that if we trade it for 2 points in space and only talk about momentum, then this is connected to this other object, this dual object that Tim described was
mm,
kind of like the shapes inscribing each other, related in that way,
mm.
and that there's like a one-to-one correspondence to it. But now we've kind of abandoned this notion of momentum, by moving to this dual space, and by abandoning the notion of momentum, we've abandoned this idea of points in space in any kind of physical space that we are familiar with, and then that's where the magic happens.
Mm.
Yeah.
So
I,
oh, go ahead,
I would
Tim.
say the details are of course very complicated for amplitude. You pretty much need to have a PhD to get the detail on this. But it's not totally intractable. So in this amplituhedron business, the number of particle is just how many sides you have in this shape, right? And so as you can
Mm,
imagine, the difference between 4 particles versus 5 particles is just maybe how many edges, how many sides you have in this shape. And of course,
mm,
and let's say you have a process where 3 particles comes in, 2 comes out, and then those 2 again turn to 5 particles. And in ordinary space and time, it's a very complicated process, right? Like particles come in, do all these possible things, quantum physics, particles come out, do all this. But if you view it in the amplituhedron space, it's basically like stacking multiple, um, not literally, but in analogous way, it's almost like stacking a cube and like octahedron together. You glue some of the sides together, then lo and behold, hey,
mm,
you can combine processes, right? And so for now, it's really a language that makes some of these things a lot simpler. It makes some of these quantum mechanical operations almost much more cleaner and more apparent.
mm. like one train of thought that I was thinking of as we're discussing this is that even like the notion, I guess like I'm trying to understand what does a particle mean in this type of context? Because the same argument you guys gave about, oh, if I try to like pinpoint space and time itself at like a particular instant, it will destroy itself. The same thing can be said about a particle. If I throw enough energy at it, it'll just destroy itself. And so I'm wondering, like, I guess how does that change? Like, because you still have the same issue that carries forward, or does this not claim to solve that issue? This is just simply moving space and time and replacing the notion of particles with a geometric kind of picture.
Yeah, well, yeah. Let me clarify this, right? Like the
Mhm.
Amplituhedron program so far does not solve any of the problem we mentioned that space-time destroy itself
Mhm.
because it
Mhm.
is not a new theory. What it does is, can you have what it aims to do is, can you have a theory without any reference to space-time? Of course, space-time still destroys itself, but these theories, they're
Mhm.
not theories of quantum gravity, right? So if you ignore gravity, this doesn't happen. And of course, you can argue that if you ignore gravity, not so, like, what's the big deal of mentioning space-time, right? But so,
Mhm.
like I would say amplitude is a proof of principle. It's telling you that,
Mhm.
hey, if you just change your mind, change the way you view the world, you can think about the world, or these toy worlds, you can think about the world without space and time, and it still makes sense.
It's a
But
really tough question that you ask, like, because like we're used to defining particles as having locations in space and time. So if we remove space and time, you're saying, how can I think of a particle? Um,
Yeah.
and kind of expecting some kind of intuitive answer, but the answer will almost by definition be non-intuitive, right? So we could say that maybe instead of thinking about a particle as kind of like a ball that exists in a point in space, maybe it's more natural to think about it as a line in a twistor space. Um,
Mhm.
that's not satisfactory in terms of giving one a sense for how they should think about a particle, but um, kind of the whole point of this was to destroy um, the familiar notion of particles. So it's difficult to expect a familiar answer to that question, I would say.
That's That's fair. I guess like if I'm trying to think about this as intuitively as possible, is it essentially sort of taking like you kind of take all of space, all of time, and you perform this transformation, and then it gets replaced with the geometrical object itself? Because you're not like saying, oh, within the this like from this time to this time, and this spatial location, this spatial location, I apply, this amplitude-hedron business, and then like get my answer. It's literally like the entire space and all of time in this object.
Yeah, it's
Is
almost
that?
like, let's say you have like a VR simulation, right?
Mhm.
And like you can describe the whole universe of the VR simulation in terms of like the physics engine, but then you realize that you can think of this physics engine as a set of computer commands, which is like the Unity or whatever program you're using to make the virtual reality simulation.
Mhm.
And let's
Mhm.
say that this computer, this whatever computer language, I guess C#, if it's Unity, that you can use that language to recreate all the physics but it also describes this whole new layer of what's going on, underneath the simulation.
Mhm.
So then you can say like, well, okay, so what's an object? How should I think of a Unity object now that I'm aware of this C# code? You could literally think about it as maybe some abstract class defined in some directory of some source code that's been turned into an executable or something, right?
Mhm.
But there's we're talking about a way to describe it that's outside of the simulation. So it's going to have some external uh, rooting for the description.
I- mhm.
Yeah, I also want to add
Oh, go
that,
ahead, Tim.
like in terms of quantum physics, because remember, we are still part of the universe right now. The experiment
Mhm.
began, let's say, at the Big Bang. It's still going on. Like, it has not ended. If you believe the universe is computing the amplitude, we are still part of the amplitude. So even the fact that we think our hand is here, or we're having this chit chat, it is still part of the quantum calculation. And it's, of course we can think of it in terms of space and time, but if you buy into this amplituhedron business, maybe we are part of this geometrical shape, and I don't know how you would call that. It's not evolving in that way, because space and time is just, I don't know, all mixed up in this picture, right? It's all like there's no space and time, but we're just this geometric object. I guess it's almost impossible for us humans to think about it, but at least we can get a sense. Like, it's, if you like this directive idea, it's like all these geometrical object directives since the beginning of time, and we're still part of it right now. I don't know if that makes it any better or worse, or more intuitive or less intuitive.
Yeah, I actually like the analogy you gave, Mikey. So are you saying this like, I guess an analogy for like what Amplitude like hopes to achieve is as if the universe is this like you can think of it like a video game where I see like, a character moving in space and time, but that's not actually what's happening under the hood. It's actually a bunch of ones and zeros moving all over the place. And so this is sort of the underlying language that describes like what we see. Is that essentially what you're trying to say?
Yeah,
In
yeah.
some
So like
capacity?
if Tim mentioned Tim gave the analogy of like, thinking about this as like, or the description of space and time is like finding a bug in the matrix. Well, if you really want to understand that bug, maybe you gotta, dig a little deeper into deeper layers of the code as opposed to just the surface level one that we have access to. But and maybe you'll find an explanation there.
Yeah. Yeah, we're almost at time, and there's another audience question which I want to ask after we, wrap up this episode. So to I guess to conclude things in our usual tradition, how would you what words of wisdom has the Amplituhedron taught you that you'd like to share with the audience?
That is a tough question in some sense, because how do I put this? It's a decades old. And when and this happened when I was a grad student, and man, when it came out, I was so interested in it. Although I probably lacked the capability to do deep research in it, but I still hope to follow closely. And probably, I would say it probably is not the true answer. No doubt, because I doubt that we have 100% of the story, right? But it is remarkable that if you take this drastically dramatic view, almost like integrating all of space time, everything all together, completely flip it inside out, upside down, and somehow something even more beautiful, something more beautiful, even simpler emerges. I mean, that's mind-boggling, and it gives me conviction that reality, there's probably more to reality than we think. There's probably something even crazier that we haven't discovered yet. And I really hope that, I get to live to see what that really is, or close to a vision of that. That's super exciting. Yeah.
Yeah, I guess no real words of wisdom for me. I just wanted to I guess one thing that we've had a lot of episodes about a lot of different topics, but in terms of like current research, um, this is the most exciting thing happening. I would say in terms of like people talk about the dream of physics, the goal of trying to find a theory of everything. This is really where it's at. I can't say that with certainty, but um, I mean, and actually, like, yeah, the single object that, it actually does give rise to aspects of gravity as well, and is tied to that. We haven't talked about that yet. But, it ties all of these things together that physicists have been having difficulty even thinking about in the same framework. And it does a lot of it by accident. So in terms of like, if research topics were like stocks, I would, yeah, this is one worth investing your emotions in.
Yeah. So before we end this episode, one audience question that I promised to ask at the end was, do you guys still do physics research? To either of you, or actually to both
No,
of you.
yeah, it's been a while since I last put something out, 2 years, but yeah, we'll see. It's never
Yeah.
really over. It's not like being an athlete where you have some prime stuff.
Yeah, I would say true academic research definitely no, but once you go through the physicist training, I think you always have that mindset. You always think like a physicist. So yeah, the real answer is no. I don't have the time nor the energy nor the collaboration to really do real academic research, and it's really tough. Honestly, it has to be a full-time endeavor. Like unless you're crazy, unless you're a superstar, maybe, but not for me. But still, I think it's important to still keep up with the interesting stuff, because like this is what, like I think is it David Kaplan, he said, like this is the stuff that makes us humans, and this is the stuff that's worth almost like beyond any economic measure, right? This is the stuff that's worth more than money, basically.
Yeah. Well, I mean that satisfies me for an answer. And so that on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you all.